So I told you one type of problem, right? Pick up. Usually in electron in a graphene, electron in graphene can be thought of two-dimensional gases, okay, with energy and momentum relation. So E is equal to P into C. E is equal to P into C. Why? I mean P into V, isn't it? Pick up, not P into C, or V into P, mod of P. Why? It's a relativistic particle. Not completely. Don't take velocity is equal to C, then it will become photon, isn't it? Because it's not completely like photon, but it's a relativistic particle in a graphene. Am I right? I told you. So graphene means two dimension. They don't mention that graphene is two dimension. That you should judge that one. At least nano wire means one dimension. Graphene means two dimensional layer. Okay. So metal or something usually three dimension like that. I mean dimension is also important. Am I right? So dimension is equal to, speak up, 2 here. Okay. So then E is equal to V into, this is h bar into K modulus. Okay. Magnitude value. H bar into K, I mean K power 1, isn't it? So I'll write as just V into P. Okay. Magnitude of P is equal to h bar into magnitude of K. Okay. Pick up. So that's why D is equal to 2. Pick up. Then S is equal to 1. Okay. Rho of E is equal to some constant. I mean, what he's asking is, okay, if rho is the number of electron per unit area. Pick up. What he has given is, let me write down, S is equal to 1. Okay. Rho is equal to number of electron per unit area. Okay. Pick up. Then energy per unit area is proportional to rho. I mean, energy per unit area. E by A, how it is proportional to rho. Rho power what? This was the question. I think yesterday I told you, right? These kind of questions are there. Okay. It's very simple. Okay. How do you start? Speak up. So first you need rho of E, isn't it? Speak up. Shall I write it here? Rho of E is equal to constant. Volume is there. Not volume. Area will be there. Am I right? Speak up. In rho of E, this is a two-dimensional case. Okay. Area will be there here. Area into, speak up, some constant into E power D by S. What is D? 2 by 1 minus 1 dE. Is that okay? Speak up. That's equal to area into constant into E into D, isn't it? So can I write like this? Speak up. Then first thing that I need to find is, okay, energy per area should be written in terms of number per area. Now you go for number one, okay, 0 to EF. You can do 0 to EF, even though they are not mentioning 0 degree Kelvin. Did they mention 0 degree Kelvin? No, they don't mention. But you can do it at 0 degree Kelvin. What is this one? This is equal to rho of E d. F of E is equal to 1 here. Got my point? Okay. F of E is equal to 1 here. 0 to EF. Okay. Rho of E d. So let me write it quickly. Okay. Area into constant into EF square by, speak up, 2. Number per area. Okay. That depends on what you call constant into, speak up, EF square by 2. Okay. That means EF proportional to number per unit area whole power 1 by 2. Okay. That's one expression you got. Okay. So next thing is energy. Energy is equal to integral of E rho of E d. F of E was there, but F of E equal to 1. Am I right? Speak. E F of E rho of E d 0 to EF. 0 to EF, speak up. F of E equal to 1. Is that okay? Speak up. So then what will happen here is, speak up, 0 to area into constant into 0 to EF. Okay. E square d, that's equal to area constant, speak up, EF cube by 3. Okay. When you take this area here, EF is proportional to energy per unit area whole power 1 by 3. Okay. Speak up. What is this expression? Fermi energy proportional to number per unit area power 1 by 2. Okay. So then can I write like this? Pick up. So what I can write now? Speak up. These two are proportional, isn't it? Speak up. Energy per area, speak up, proportional to, I mean 1 by 3 proportional to number per area power, speak up, 1 by 2. So that's why what you can write, energy per area proportional to number per area whole power 2 by 3. 2 by 3? 3 by 2. 3 by 2. Very simple. Got my point? Quite frequent question. I think twice they asked. Okay, pick up. So option, I think option 1 here. Okay, speak up. Option 1 here. Okay. So shall I proceed? I hope I told you this kind of question. Not only this one, you just pick some other question. Is that okay? So yesterday's problem, I told you. I mean this particular problem. I mean you can think in K space, isn't it? I was telling this problem. You don't have to what you call. If you solve for EF again, you have to write EF in terms of Fermi wave vector or something, isn't it? Pick up. I mean, he's asking what is this one? Fermi wave vector here, isn't it? Speak up. So that's why what I will do here is, okay, I'll come to this problem. Okay, I'll come to this problem. First, we shall think like this. Okay, speak up. What was this one? Okay, rho of K vector, d cube of K vector. Am I right? Speak up. Number of translation state, isn't it? This is number of translation state whose K vector ranges from K to K plus dk. V by 2 pi the whole cube. First I'll do for 2 dimension, then I'll do for what you call, sorry. So first I'll do for 3 dimension, then 2 dimension. Okay, d cube of K, isn't it? Number of translation state, isn't it? Now look at here. What happens is at t equal to 0 degree Kelvin, okay, at t equal to 0 degree Kelvin, all states within Fermi level are completely filled. Am I right? Actually, again, we have drawn only this graph actually, isn't it? Pick up. So f of e as a function, this is EF, isn't it? As a function of e, isn't it? At t equal to 0 degree Kelvin. Now what we have to do is we need to think in K space. Okay, in K space, what will happen is, okay, so if I take K space, this is Kx, okay, Ky, Kz, okay, speak up. In K space, all levels within one Fermi sphere is completely filled. Got my point? So here, so energy less than EF are completely filled. Am I right? Speak up. Energy less than EF are completely filled. In the K space, magnitude of K less than Kf. What do you mean by this region? What is this region? K, magnitude of K less than Kf. What is that region? That's one spherical region. Got my point? Where K equal to root of Kx square, Ky square, Kz square, isn't it? Pick up. Here E less than EF. Here we don't think about any space or something, but here K is a vector. Am I right? Pick up. If magnitude of K less than Kf in 3 dimension, that will make a sphere, isn't it? Of radius Kf. Can I write like this? Because now at 0 degree Kelvin, okay, all of these state within this one are completely filled. Got my point? All of these state within this one are completely filled. Completely filled by the particles. Are you getting my point? Pick up. Completely filled by the particle. Okay. All of the state outside that one are completely empty, just like here. Is that okay? Because probability is 0, occupation probability is 0, isn't it? Pick up. So then what you can do is, okay, what you can do is to find the number of particle. You can find number of particle directly here. So see this one carefully. Okay. So number of particle, okay, that's nothing but number of state here. Can I say like this? State within this one, because all particles are within this one, and all of the states are completely filled at t equal to 0 Kelvin. Okay, so that's why now counting number of states within this one is nothing but counting number of particle. Counting number of state. This is a count of number of state actually. Later we took distribution of the particle. We counted number of state in the density of state idea. Okay. Now here counting total number of state within the Fermi sphere, that is nothing but counting number of particle. Degeneracy should be taken care because this is only translation state. Because when we talk about electron, okay, so each translation state can be occupied by 2 electron. Am I right? Pick up. That's why again you should take care of that one. Okay, pick up. I'll write for electron. Okay, 2 into what I do is I'll do rho of K vector. Pick up d cube of K vector. Okay, within the sphere. Sphere of radius kf. You got this idea? Speak up. Count again. Here what I did, I counted number of state within the Fermi sphere, total number of state, okay, within the Fermi sphere. That count is nothing but, I mean, you have to multiply by 2 if you have electron, okay, pick up, because this is a count of only translation states. Spin states are also there. This you matter. Is that okay? Then I will again, how if you integrate this part, okay, within a sphere of radius k, what will happen? This is d cube of k within a sphere, that is 4 by 3 kf cube. Got my point? This number is equal to, okay, 2 into, what is this one? v by 2 pi the whole cube. Is that okay? 2 into v by 2 pi the whole cube. What is this one? Integral of d cube of k within the sphere, that's nothing but 4 by 3 pi kf cube. Got my point? Here you directly got that expression. What was the question actually? Wait a second. I'll just take the question now. Okay, speak up. What happened? I got n is equal to, speak up, 2 into, I mean, you should be able to write this expression directly. V by 2 pi square, speak up, 4 by 3 pi kf cube. Okay, speak up. You should be able to write this expression. Now you can take V here, you will get number density, isn't it? 2 pi the whole cube here, am I right? Speak up. V by 2 pi the whole cube. You got this idea? If you can write this expression, I mean, if they ask anything about Fermi, what is the wave vector, you can directly do that. You don't have to, what do you call, go to EF again, substitute that dispersion relation. That would be quite lengthy process, isn't it? Speak up. So I think this part is irrespective of dispersion relation. Check this out. Check this out. This idea is irrespective of dispersion relation. Dispersion relation didn't appear here. Directly we did this one. There you need to do density of state, you need to use dispersion relation, everything, isn't it? Pick up. But for Fermi wave vector, it is not required. Okay, just think over it. Now, again, in case of 2 dimension, how do you do? Speak up. In case of 2 dimension, in case of 2D, the same thing, number of particle is equal to, speak up, area by 2 pi the whole square, factor 2 if it is electron, okay, pick up. Then integral of d cube of k within a Fermi disk, you can say. Again, in case of 2 dimension, suppose if I take kx and ky here, okay, speak up, you have a disk of radius kf, okay, all of these state within that one is completely filled at t equal to 0 degree Kelvin. You got my point? T equal to 0 degree Kelvin, okay, speak up. Then counting number of state within that one is nothing but counting number of particle, take care of spin degeneracy. Got my point? Okay, what is the area? Pick up 2 pi pi into, pick up, pi into kf square. Okay, you got this expression directly. Is that okay? So how to crop this one? So let me write this expression again. Now we shall go to that question. Where is that question? You can see this question? Thin metal film of dimension, so 2 millimeter cross 2 millimeter. So can you see this one? This is fine. Should I make it little larger or this is fine? This is fine, am I right? Speaker. Area is given. Okay, area is equal to 2 millimeter cross 2 millimeter. Okay, then number is given. What is this one? 4 into 10 to the power, speak up, 4 into 10 to the power 12 electrons, isn't it? Magnitude of the Fermi wave vector of the system in the free electron approximation. Okay, speak up. Then what would you do? What I have written for 2 dimension, n into 2 electron. Okay, but that area divided by 2 pi the square, that d square of k, okay, that should be integrated over Fermi disk, you say like this, okay? That's equal to pi into kf square. I think this will give you very quick answer. Kf square, that's equal to, speak up, n by a 2 pi the whole square divided by 2 pi, okay? Speak up. What is this one? Kf is equal to root 2 pi into root n by a, okay? I hope this is the answer. Check this out, isn't it? That okay, how simple it is. Thinking about that k space, okay? And counting number of state, this is actually count of number of state within the Fermi disk. With taking care, I mean, when you multiply by 2, you counted all state, including spin state. Actually, each state can be occupied by, can have 2 spin state. Am I right? Because just like your hydrogen helium atom and all. Am I right? 1s2, you put 2 electron over there, isn't it? Just like that. You double it. That is the count of number of particles. Okay, speak up. Can you write it directly? Speak up. No. What I'm saying here is, so I mean, in this expression, okay. So in this one, okay, we think only about energy, am I right? At 0 degree Kelvin, EF here, okay, 1 here, F of E here. We think only about energy here, isn't it? So that means all states for which E less than EF are completely filled. Am I right? Completely filled. All states E greater than EF are completely empty, isn't it? Speak up. So then look at here. The same thing, if you write this expression for in terms of K, E is usually in terms of modulus of K power some S, am I right? Speak up. So E less than EF means K less than KF. Speak up. That means if you go for K space, K less than KF means what? That is a sphere, am I right? Because K, I mean, in case of 3 dimension, what is K here? Root of Kx square plus Ky square plus Kz square. What do you mean by this K less than some value? That's a spherical volume region, isn't it? Think in spherical polar coordinate. Speak up, isn't it? So that's how I just argued. Okay, I mean now what will happen at 0 degree Kelvin? Okay, so if you think of K space, there are states. Am I right? I mean, what do you mean by K space? For particular Kx, Ky, Kz, you have space actually. Actually, in condensed matter book, they will start with K space. They put some points and all, and then they define density of state. Okay, I went with Reef idea. Okay, speak up. If you take Kx, Ky, Kz, okay, if you take a Fermi sphere of radius Kf, okay, all states K less than Kf are completely filled, means all states within this Fermi sphere are complete. This is sphere. I mean, this will talk about spherical region, isn't it? Mathematically. Speak up. Are you getting the point? All of the states within this Kf are completely filled at 0 degree Kelvin. States are there. They are completely filled by the particle, all of the states. Now you count the state, that will be the count of number of particles. But double it by spin degeneracy. We are talking about only spatial state here.
They don't mention anything about, they don't mention electrons.
No, then you don't double it. Usually they'll mention electron. Okay, you don't double it. That's it. Okay, speak up. Usually they mention. I mean, practical questions actually. Those are very practical questions. They'll mention it. Okay, speak up. Yeah. So shall I move on? Yeah. So that question should be answered without what do you call? So for an ideal Fermi gas in 3 dimension, the electron velocity. Okay, I'll do like this. Okay, problem. That's better. Give me a couple of days. Okay, I'll be practice with this. Okay, for an ideal Fermi gas in 3 dimension. Okay, D equal to 3. Okay, velocity. I mean, he didn't talk about relativistic, non-relativistic. You don't overthink. You have to take non-relativistic. Okay, speak up. E is equal to h bar square k square by 2m. Got my point? Okay. For an ideal Fermi gas in 3 dimension, the electron velocity Vf at Fermi surface is related to concentration. He's talking about concentration. Am I right? Then you can apply that idea. Okay, n dimension is equal to 3, n is equal to what is this one? Speak up. He said electron, no, Fermi gas. He said Fermi. Anyway, he's talking about proportionality here, isn't it? Speak up. N is equal to R actually velocity. Am I right? This is nothing but half mv square. Speak up. Now EF is equal to, that's equal to h bar square kf square by 2m. Okay, that we write it as half m vf square. Got my point? Speak up. So now look at here that what would you do? Would you integrate this one? You can integrate this one. What you can do? N is equal to, speak up, integral of speak up, or you can first define rho of e. Rho of e is equal to volume. You need volume term. Okay, speak up, into e power d by s minus 1, and you can use this one. N is equal to 0 to ef. F of e is equal to 1. Speak up. F of e is equal to 1 into rho of e into d. You can do this one, and you can take volume term here. That is a now concentration. Okay, concentration means number per volume. Okay, so or what I told, I mean, so here once you write this concentration n by v, I think if you do this one, what is e power d by s minus 1, 3 by 2 e power root e. Am I right? Pick up. That's equal to constant into, pick up, ef power 3 by 2 divided by 3 by 2. Pick up. Now ef, you can do this one. ef proportional to n by v whole power 2 by 3, but vf is, speak up, proportional to root ef. Can I write down proportionality just like class 12th we used to write like that, right? Vf proportional to root ef. That's why that is proportional to root of this one, n by v. Speak up. N by v whole power 1 by 3. This also okay, because you need to talk about proportionality here, isn't it? Got my point? I don't think you better you can do here only, because not much big deal. But for me, wave vector you better do directly. Okay, or you just think over it. Okay, think over it. Do it in a different manner. Okay, do it in a different manner. Now what I'm saying is, okay, now you write that expression directly. What was that expression? V by 2 pi the whole cube 4 by 3 pi kf cube. Sorry, am I right? 4 by 3 pi kf cube, isn't it? Pick up. That's the volume. Now h bar into kf is nothing but pf. Okay, pf is nothing but m into vf. I mean, these relations you can. That kf is proportional to vf. Am I right? Pick up. That's why you can write directly n by v whole power 1 by 3. That is proportional to kf. Okay, that's proportional to. This also gives you direct idea. Got my point? Pick up. Think that one. Think over it. Whatever I told. Okay. Yeah, I think this is one more question. Consider a non-relativistic. Pick up. Two-dimensional gas. Okay. D is equal to 2 of n electron with Fermi energy EF. Okay. Two-dimensional gas, non-relativistic. That's why E is equal to, pick up, h bar square k square by 2m. I'll take it like this. Okay. What is the average energy per particle? Average energy per particle. Okay. Average energy per particle at t equal to 0 degree Kelvin. Okay. That means what you have to do? Speak up. First, I'll find rho of E. That's equal to, is a 2 dimension. Rho of E is equal to area comes in 2 dimension, constant into e power d is 2 by 2 minus 1. Speak up. D. Okay. Rho of E, that's equal to, speak up, area into some constant into E dE, isn't it? Can I write like this? Sorry. 0, am I right? Independent. Give me 1 minute. 0. Just dE, isn't it? Speak up. Then you need to do these two actually. Number is equal to 0 to Pick up 0 to EF, okay, rho of E d. He said electron, okay, it doesn't matter when you take the ratio that factor 2 will get cancelled, okay, but still take the factor 2. What do you think? No, wait. I mean, average energy per particle, he's asking, okay, pick up. So this is average energy. That's equal to 2 times 0 to EF, speak up. E into rho of ED. F of E is there, but it's equal to 1. Is that okay? Speak up. Now what you need? You need E divided by N. Average energy per particle, isn't it? Pick up. So this 2 get cancelled, that this will get cancelled. I think 0 to EF, okay, ED divided by 0 to EF D, very simply. This is EF square by 2, EF 1 by 2. Check this out, 1 by 2 EF. Or, yeah, do it again. Energy per particle, that's what he's asking. That's equal to EF square by 2 divided by EF, okay, that's equal to half of EF. Is that okay? Half of EF. You have that option, okay. The option, is that okay? Don't miss this one, very frequent question, okay. Yeah, now we shall get into specific heat. What is the time? Okay, specific heat, okay. I will quickly write the formula. You guys tell me the dependency. I don't remember completely, okay. Speak up. Electronic contribution to specific heat, the idea generated out of this one actually, okay. At what do you call 0 degree Kelvin, it is the distribution f of E, isn't it? Pick up as a function of E. This is EF here, okay. At speak up. At T greater than I mean even at room temperature also, okay, it will be like this actually. Am I right? It will be like this. Am I right? Only these fraction of the electron will contribute to your electron specific heat, isn't it? Pick up. And that we found actually, okay. I mean, the actual value we have to integrate this one, okay. We have to integrate this energy expression. What is this one? 0 to infinity. F of E, rho of E, F of E into E F of E, rho of E d. Am I right? Pick up. Factor 2 for electron, okay. E F of E, rho of E d. Then for specific heat at constant volume, that's equal to dou E bar by this E bar. Am I right? Pick up by dou V. Dou E bar by dou T. You need to do this one actually, okay. But I think we did some jugad idea here. Am I right? We found what is the fraction of the electron that will contribute to specific heat. That fraction of the electron behaves like a classical particle and all in Reef. He has done some jugad idea, okay, to show that one, okay. But what you need to remember, CV is equal to, I'll write A into T. It is proportional to T power 1. What I need is, what is this A proportional to? That depends on Fermi level, is Fermi energy. That Fermi energy depends on, speak up, density of the particle. Got my point? This is an electronic contribution to specific heat. But you should not only remember this proportionality, temperature term, you should remember what A contain. Can you tell me? That contain, I think, your mu naught in the denominator, mu naught or EF. Check that out. That you should remember. Can you check that out if you have written the expression? Because on this one you can find 3 to 4 questions actually, okay. I mean you are saying pi square by 2 A K N N, what is N? N, will N come? So mu comes in the denominator, that I remember. Speak up. Reef expression. Have you written? N is there in the numerator. Okay, it is specific heat for total specific heat. Am I right? Speak up. N into T? No? It is there like that? Speak up. That expression is important. I mean, its dependency. I'm just worrying about its dependency. Electronic specific heat. He has shown this expression. Okay, specific heat, molar specific heat. Okay, speak up. If you write molar specific heat, speak up. Then what will happen? I think 3/2 R molar specific heat, that's equal to 3/2 R pi square by 3 pi square by 3 kBT by mu naught. Okay, mu means EF. Molar specific heat. Okay, now what I need is, I need this one. Very important part here is, okay, I need you to observe this dependency, or that's equal to EF, that comes in the denominator. EF depends on number density. We have seen earlier problems, isn't it? Because how EF is proportional to number density and all. On that one, you can find many questions here. Okay, not only just to say that specific heat proportional to T power 1. Yeah, question. Speak up. Or you write EF over there. Okay, you write EF only. Is that okay? EF only. So shall I proceed? Now this is in case of electronic specific heat. Okay, nothing much is asked. Either, I mean, this relation, or what you call on that one. Okay, if density is changed, how electronic specific heat will change, like that. Okay, that kind of question we shall handle those questions. Okay, but in case of this Debye theory, speak up. Go through the video. Okay, I mean, there are many very well designed questions on those things. Okay, right now I don't have time. I'll go to problems. Okay, in Debye theory, not only what you call doing the last expression. Okay, speak up. You need this one also. What is this one? Do you remember? 0 to omega d, Debye frequency definition. Rho of omega d omega, that's equal to number of modes. That's equal to number of modes. Give me 1 minute. Okay, that's better. Speak up. 0 to omega d, rho of omega d omega. This d is the omega d is the highest frequency. We call it as Debye frequency, isn't it? This is equal to number of modes. Number of modes actually. Okay, or number of degree of freedom actually. Number of degree of freedom. In case of, speak up, do you remember, in case of our, it will be 3n, in case of n particle in 3 dimension, but you need to take 3 here, polarization state of phonons. That 3 will get cancelled actually. Got my point? Now here, this omega d, its proportionality with n by v will come, because rho of omega, speak up, can I write that contains volume? This is nothing but rho of m, right? Rho of omega, rho of v are similar. Pick up volume, some constant into omega power d by s minus 1. Can I write like this? Why not? Because E is equal to h bar omega. Only h bar is difference, isn't it? Look at here how I'm handling the problem. I'm not getting into full detail now. Is that okay? Speak up. So now, I mean, when you substitute this, what is the dimension usually? V into constant into what is the dimension? 3 by 2. If I take phonon, E is equal to h bar into E is equal to P into V. E is equal to P into V for phonon. Okay, V h bar into K power 1 actually. Isn't it? I mean, phonon, I mean, that dispersion relation is equal to E is equal to, speak up, or you can write omega is equal to, speak up, V into K. Simply we write like this, isn't it? Got my point? That is the dispersion relation for phonon, just like photon, but travels with a finite speed. That's the only difference. Okay. So when you do this one, okay, speak up. Now, what is this one? This is equal to V constant into omega power 3 dimension, okay, divided by 1 minus 1. Am I right? What is this value? Rho of omega is equal to V constant omega power square, omega square here. Am I right? Speak up. Omega square here. Now when I substitute here, anything missing? So keep the track, okay? Speak up. 3 into volume term comes outside, constant comes outside, 0 to omega d, omega square d omega, that's equal to 3 into n. This 3 got cancelled. Okay, I need omega cube by d, isn't it? Pick up. That means omega d proportional to n by v whole power 1 by 3. Am I right or not? Can you check that out? Right, am I right? Pick up. This is where they may ask question. Okay, speak up. Now look at here. What I have taken? I have taken 3D, 3 dimension. Okay, speak up. And I have taken this dispersion relation. I mean, these things only decide rho of omega d omega. That will decide everything, isn't it? Got my point? Okay. Just observe this one. Okay. We are talking about 3D here. Okay. And this dispersion relation. Is that okay? For those things, it happened. This happened like this. Omega d proportional to n by v whole power 1 by 3. Okay. So not over. Not over. Okay. This is one part. I mean, which is a what do you call some intermediate part of our Debye theory stuff, isn't it? Pick up. Next thing is they are asking specific heat for different dispersion relation for spin waves in ferromagnetism and different case actually. Okay, that's why what we need to do is we need to now. I mean, what do you mean by debate? The very basic stuff is f of e is equal to speak up 1 by e power beta e minus 1. Why? Because phonon follows photon statistics, isn't it? I'll write in terms of energy. There we have written in terms of omega, am I right? Little bit condensed matter approach. I'll write in terms of energy. Why not? I need only temperature dependence, isn't it? Speaker. F of E is this one. And again, depending on dimension and S here, okay, you find rho of E dE. Is that okay? That's equal to constant into e power d by s minus 1 into dE. Isn't it? You are going to find rho of dE, then you are going to find average energy that's equal to, speak up, any polarization state or something, 3 in case of phonon. If you want to put here, okay, speak up. You can put here, then E, f of E, speak up, rho of dE. Am I right? Speak up. You should able to, I mean, you don't have to do the integral accurately, but you should be able to grab temperature term outside so that you can find the specific heat from this average energy. That process is required. Got my point? We have done one in that actual Debye theory, T cube. Okay, but they are asking different dispersion relation. Is that okay? Speak up. Different dimension. Dimension may be different. Okay, and E is equal to some E may be proportional to, speak up, dimension D. Okay, speak up. E may be proportional to k power s. Are you getting a point? This may be the very general situation they may provide you. Usually dimension they have taken 3 only. Okay, speak up in the problem. Okay, but whatever. Okay, so then what you need to do here is, okay, it's actually 0 to I better write omega d. We write in terms of omega d in case of Debye theory. But again later we can make it 0 to infinity actually. Okay, speak up. Or you can write in terms of h bar omega like that. Okay, speak up. That's left to you. 0 to some ed. Can I write like this? Ed is equal to h bar omega d. Okay, because I have written in terms of energy. It doesn't matter whether you do the theory in terms of omega or energy. Okay, so then E into by what is f of E? E power beta E minus 1. Speak up into rho of E contain volume. You can take that one. Okay, if you volume or area or whatever. Okay, speak up. So constant comes outside. E divided by 0 to some final value ed, actually 0 to omega d in terms of omega, okay? Pick up e divided by e power beta e minus 1, and rho of e contain e power d by s minus 1 dE. Am I right? Pick up rho of e dE. Now what is the next step? How do you get temperature term outside? You put some beta e is equal to some x. Beta e is equal to x. Okay. So then what will happen is, I think this beta ed is equal to xd. Am I right? Pick up. Then we argue that ed divided by kbt. Pick up at low temperature. So I mean it's actually omega d actually. Okay, in the theory. Okay, that's equal to xd. This is very very high. We argue like this. You got my point, okay? I mean, so ed, that's h bar omega d divided by kb into t at low temperature, that's equal to xd. I mean, fine. I mean, this when e equal to 0, x equal to 0. When e equal to ed, x equal to xd. I'll say like this. But xd is very large. That's how we argue, okay? And we do the theory like this, okay? Average energy, that's equal to constant. Because we substitute that one, we write 0 to infinity. We say this xd is very very high at low temperature. This ed is very very high. We argue like this. Got my point? Okay. Then we make 0 to infinity. So what is this one? E is equal to x by beta into x by beta whole power d by s minus 1 dx. Sorry, I need to take care properly. How do you do? E into e power d by s, I can write e power d by s. Am I right? Because that will become 0 to infinity x by beta power d by s. Okay, d by s. Okay, then beta de is equal to dx. D is equal to dx by beta divided by e power x minus 1. Isn't it? What happened? Average energy. Now this is again, if you take that beta outside, pick up constant into t power d by s plus 1. Okay, t power d by s plus 1. The rest of the terms are 0 to infinity. Okay, I think x power d by s dx whole divided by e power x minus 1. This is one Riemann zeta integral. That's one constant. Am I right? What you need only temperature term outside, isn't it? Got my point? What happened? Am I right? B power d. That's right. Okay. T power d by s plus 1. Okay. Speak up. Then what you need? Specific heat, that's equal to, that is proportional to, I'll write proportional to, speak up, T power d by s. Okay. You got general equation while solving. You got one general equation. But be careful. I mean, we don't know how next they will ask the question. Okay. Pick up. They had coaching classes actually. Somehow they will design question. I mean, over time, how question evolved is you can't use trick. Somehow you should do like that. Okay. Pick up. That's what process should be known. Okay. Very simple process. Isn't it? Very simple process. I have written in terms of energy. Because rho of E and all we write in terms of energy. Okay. It depends on dimension as well as dispersion relation. Can I go to problem? Pick up. Can you see this problem? Total number of phonon modes in solid of volume V, that's equal to 3n. That's what I was saying. Total number of mode, they say like this. Okay. Pick up 0 to omega d, g of omega d omega, that's equal to 3n. I mean, g of omega, usually they will make it at per unit volume. I told you yesterday, isn't it? Pick up, they will, in many textbooks, they will define per unit volume. Okay. Pick up. So, the Debye frequency, what is asking is the number of primitive cell, omega d is the Debye frequency, and density of phonon mode. Okay, g of omega also he has given. Okay, what you need, if density of the solid doubles in a phase transition, okay, then Debye temperature is. How do you define Debye temperature? Okay, h bar omega d, that you have to read it as k b into td. This TD, we write it as this, what is this one? Theta D. He has given everything here. He has given whatever you need to do the problem, okay? 0 to omega D, okay, he has given what is that G of omega. So A V into, pick up, omega square D omega, that's equal to 3 into N, am I right? Pick up. That means omega D cube proportional to N by V, am I right? The same thing happened. Omega D cube by 3, V volume goes here. Got my point? Okay, so or omega D, speak up, proportional to N by V whole power, speak up, 1 by 3, isn't it? Speak up. What I need, I mean, if omega D proportional to this one, TD also proportional to the same thing, because omega D proportional to TD. This Debye temperature, Einstein temperature, everything, Fermi temperature, you can define. Can you find the pattern over there to define? Is that okay? Speak up. So that's why, so TD proportional to omega D proportional to 1/3 of, I mean, 1/3 power of N by V. Pick up. Now, in some phase transition, okay, pick up. What is that? Density of the solid is doubled. Okay, if density doubled means, pick up, it will be, pick up. I'll write TD1, that's proportional to N by V whole power, speak up, 1 by 3. Okay, this TD2, that is proportional to density doubled, 2 N by V whole power 1 by 3. Proportionality constant is same. Okay, then what is asking? Debye temperature TD2 divided by TD1, that's equal to 2 power 1 by 3. Am I right? Speak up. That will be increased by a factor of 2 power 1 by 3. Am I right? Cross check this answer. Do it again. Okay, do the problems again. Cross check the answer later. Okay, it's there in the web page. Okay, speak up. It increases by the factor of 2 power 1 by 3. Very simple. Okay, that's what I'm stressing. Even in the derivation, what you need to look into. Okay, that's very important. That okay. Fermi energy of two metal X and Y are 5 electron volt and 7 electron volt. Okay, pick up. I'll write EFX, that's equal to 5 electron volt. Okay, EFY is equal to 7 electron volt. Okay, pick up 5 electron volt, 7 electron. And the Debye temperatures are, okay, can I write TD? Pick up, TD is equal to 170 K, TDX, okay, TDY is equal to 340 K. The thing that I forgot to mention is, okay, speak up. I mean, usual Debye theory, okay, Debye T cube law. What is the specific heat proportional to T cube? But that's not sufficient. I need, what are these constants? I mean, we write BT cube usually, okay, that is BT cube. I need, what is this B proportional to? I hope this is proportional to theta D cube. Theta D means TD. So somebody correct me if I'm wrong. That is again proportional to omega D. Omega D is again proportional to N by V power something. 1 by 3. In the usual Debye theory, it's 1 by 3. Usual Debye theory means they will change the dispersion relation. That's what I'm saying. Then everything will change. Got my point? This also required. This constant, okay, it is inversely proportional to Debye temperature the cube or Debye frequency the cube. We can say like this because, I mean, you got this expression h bar omega D is equal to, speak up, kb into TD or kb into theta D, isn't it? Got my point? So shall I proceed? This is required. Okay, I think I have written the exact expression. Am I right? Pick up using Riemann zeta integral answer and all. Okay, have a concentrate on this one. Okay, what is this B? Okay, pick up. What does this contain? That's very important for me. Okay, so because once theory may be advanced physics theory, but questions will be on the dependencies usually most of the case. Just check that out. Okay, pick up. That's why that knowledge is required. Not only that, you should know. Suppose if some gimmick they do, changing the dispersion relation, changing the dimension and all, then also you should be able to do the theory. Okay, speak up. So that's why I have just record that one. Okay, speak up. Now the molar specific heat, okay, molar specific heat of these metals at constant volume at low temperature, that's equal to gamma x T Ax T cube, Cv gamma y T Ay T cube. Okay, gamma and A are constant. Assuming that thermal effective masses of the electrons in two metals are same, okay, speak up. I mean, usually that will not be same in condensed matter phase. Okay, speak up. Which of the following is correct? Okay, he's taking gamma x divided by gamma y. Am I right? Speak up. And ax divided by ay. Speak up. So again, if you write specific heat like this, I mean molar specific heat, am I right? Speak up. That's equal to gamma T plus A T cube. That's how he has it. Am I right? Speak up. Now this gamma inversely related to Fermi energy, isn't it? I mean, this is a contribution due to electron. You got my point. Pick up. Is that okay? Now for metals, okay, specific heat that's equal to, I write AT plus BT cube. They may change the coefficient. You got my point? Okay, I'll write AT plus BT cube. Okay, the thing that you need to remember, A is proportional to 1 by EF. 1 by mu naught you will come, am I right, in the electronic contribution, isn't it? Pick up. So B is proportional to 1 by theta d cube or 1 by omega d cube. These things you should not forget. Got my point? So what I'm saying here is, okay, this one is electronic contribution. Okay, this one is phonon, lattice contribution. Got my point? So shall I proceed? This gamma, you should quickly find, this is what you call electronic contribution, this is phononic contribution. That coefficient inversely proportional to EF, this coefficient inversely proportional to TD cube, am I right? D by temperature. I'll write TD, not theta D, okay? So that's why what he is asking then, gamma x divided by gamma y, isn't it? That's equal to EFY divided by EFX, because that is inversely related. Speak up. Very simple question. Then you can find this one, am I right? Speak up. What is this one? Speak up. EFY divided by EFX 7 by 5, isn't it? Pick up. Simply that's equal to 7 by 5, isn't it? Pick up. Then AX divided by AY, that's equal to T dy cube divided by T dx cube. Okay, inversely related to cube of the Debye temperature. Okay, can you do this one? I hope hint is sufficient. That you need to do. Okay, I mean, I think what is that? 340 cube. What is 340 divided by 170? 2. That's 2. So 340 divided by 170. The cube 1 by 2 cube, that is 1 by 8. Am I right? Pick up what? Which one? This one, B, isn't it? 7 by 5 came here.
7 by 1 and 8. First option.
Okay, what AX by AY? Okay, 2 cube. Yeah, that's right. Okay, do it again. Do it again. What was this question? Suppose frequency of phonon in one-dimensional chain of atom. Okay, one dimension. Okay, D equal to 1. One-dimensional chain of atom. Okay, so mark down one-dimensional chain of atom proportional to wave vector. Okay, that means frequency the omega proportional to k power 1. That means S is equal to 1. Speak up. Then the Debye frequencies. He's asking directly. N is the number density of the atom. Okay, N is pick up number per length actually in one dimension what you define. Okay, number per length, okay, and c is the speed of the phonon, okay. Okay, I need this one. Omega is equal to c into k. I need to do actual problem, okay, speaker. Then Debye frequencies. How do you define Debye frequency? 0 to omega d, pick up rho of omega d omega, that's equal to one dimensional chain. It will be only n actually. That's what I'm guessing. What do you think? Because in one dimension, I mean, particles can move only one dimension, only one degree of freedom for each atom. This total number of degree of freedom, or total number of mode, they will explain like this. Got it? This is just n here. Don't throw any factor 3 or something. He might have, that's what I'm also now. I mean, in one dimension, will it process 3 polarization state? Because this is not usual phonon theory, am I right? Because in the earlier problem also, he didn't take that phonon polarization state. Have you seen this one? In this one, he didn't take 3 factor. But in the actual theory, we take factor 3 here also. Isn't it? Okay, let us do this one, okay? Pick up. I mean, now look at here. How do you, I mean, you need to do this one completely. This is the density of state, rho of omega. How do you start? Speak up. Uh, rho of omega d omega, rho of omega d omega, that's equal to rho of k dk. In case of one dimension, this is equal to L by 2 pi into dk. Am I right? Pick up. Omega is equal to c into k. That's why dk by dk by d omega into d omega. Is that okay? Speak up. So what is d omega by dk? C. That's where rho of omega d omega. That's equal to L by 2 pi. Okay, 1 by c into d omega. Now don't use e power d by s minus 1. Okay, you need all factors here. Okay, speak up. Now what is this one? L by 2 pi 1 by c. L by 2 pi 1 by c d omega. Okay, speak up. L by 2 pi 1 by c d omega. Now let us do here. So 0 to omega d L by 2 pi 1 by c d omega n. Am I right? Speak up. When I do this one, L by 2 pi 1 by c omega d is equal to n. N by L, he write it as omega d is equal to 2 pi c n by L. N by L, he has written it as small n. 2 pi c into small n. Right, okay? Yeah. Let me move on. Okay, he didn't take any other thing. Okay, I mean, you should not do anything extra. Okay, so whatever he gave, I mean, that should be mentioned actually. Okay, speak up. Usually, that's very important part. Am I right? Look at here. Can you guys see this one? A temperature dependence of specific heat of two metal A and B both with both quadratic dispersion relation. Quadratic means pick up E proportional to K power 2. Okay, I mean, that's the usual one, isn't it? That's a usual one. I mean, your non-relativistic equation, isn't it? Pick up, shown in the figure. Okay, speak up. So what they have plotted Cv by T versus T square. Am I right? Pick up. Versus T square. If that is straight line, okay, pick up. Then Cv should be, pick up. I'll write beta gamma. Okay, AB he has taken out there. Okay, beta not beta. Beta means 1 by kbt. Give me some constant. AT plus BTQ. Is that okay? Speak up. Now CV divided by T. I mean metals. Am I right? He said metal. Okay, two metals. Okay, speak up. That's why electronic contribution, lattice contribution. Okay, speak up. Insulator, this part will not be there. Am I right? Only this part will be there in the insulator. Free electron will not be there. Okay, very simple. But this one A plus B T square. Speak up. If you plot this one versus T square, obviously it's a straight line passing through some y axis. Am I right? Y intercept, isn't it? Pick up. Now look at here. Y intercept is A. Y-intercept is A, isn't it? Pick up. Then what is this one? Slope is nothing but, okay, Y-intercept is equal to A, okay. Slope equal to B. This A is inversely proportional to, he's talked about effective mass also, okay. 1 by EF, okay, pick up. It is inversely proportional to omega d cube or theta d cube, isn't it? Now let us see the options. Okay, let us see the options. The density of state at Fermi energy A is smaller than that of B. Density of state, the density of state at Fermi energy of A, he talked about density of state at Fermi energy.
Number of particles at Fermi.
You can say like the average number, no, density of states, not occupation. You need much more condensed matter idea. I thought it can be done here only, okay, within this idea. That's why I placed it here. Because he talked about effective masses, am I right? Because the density of state at Fermi energy B is smaller than that of A. Density of state at Fermi energy.
Density of a state will be equal to density of particles at Fermi energy.
No, we usually, okay, in this case, okay, I don't exactly remember, okay, this rho of E, pick up rho of E versus E, isn't it? Pick up, it is root E. It's a usual non-relativistic in 3 dimension. It is root E like this, isn't it? Now you have somewhere here Fermi energy, EF. Okay, we can answer. We can answer. We can answer. Now look at here. What I'm saying here is, okay, rho of E proportional to root E, e power d by s minus 1. It's a usual one. Okay, that root E curve is like this actually. Okay, pick up. Rho of E versus root E. Okay. Now suppose metal B have got Fermi energy lower. No, higher, because this y-intercept is inversely proportional to Fermi energy. Am I right? Pick up. So again, lower Fermi energy by A, isn't it? Pick up EFA. So can I write like this? Okay. So EFB somewhere here. Pick up. So now density of state. Okay. Got my point. That okay? Now can you answer? What is that? Density of state for A is lower than at Fermi energy. Okay, density of state at Fermi energy. What would you choose? Density of state at Fermi energy of B is smaller than that of A. No, that's wrong. Okay, this is right. Okay, is it multiple answering? Which question? TAFR question, not multiple answer. But effective mass is also included. Answer A. That's right. Okay, speak up. I mean, if it is multiple answering, we would be in trouble because you should know effective mass concept also. That depends on, I think, E versus K relationship only. Effective mass. E versus K relationship. It's a derivative. Okay, second derivative will give you effective mass actually. If possible, I'll discuss. Okay, speak up. Bit condensed matter idea. That I mean, your parabolic relation E proportional to K square. Am I right? There only 1 by 2m comes. Am I right? E is equal to h bar square K square by 2m. Okay, that means that coefficient will decide what you call your curvature, isn't it? in k square curve, am I right? That coefficient will half kx square we write, isn't it? Because I mean what I'm saying here is, okay, E is equal to some constant into k square, am I right? That constant is h bar square by 2m into k square, isn't it? Because now its second derivative that will decide this one actually. Second derivative means curvature. That effective mass, I don't know. I mean, how to talk about that effective mass here. So, Indrajit, did you reply? Given answer is option. Option A is right. Okay, pick up. Option A is right. I mean, I also got this. You got my point. I think I have given some question. Plot rho of E versus E. You just point out EF. That's it. Okay. Pick up. This question you should be able to answer now. TIFR question again. Can you see this one? CV is equal to A into T power 3 by 2, okay, plus B into T cube. T power 3 by 2 plus B into T cube. A and B are constant. At low temperature, measure specific heat of some solid, okay, found to be like this, okay. What is that one due to? Now you should answer it by experience now. Got my point? Answer it by experience means pick up. What is this one is due to? Phonons, am I right? In 3D, isn't it? Phonons in 3D, isn't it? That phonons are boson. Is that okay? Pick up. I mean, look into option. One fermionic excitation, omega k. Other one is bosonic excitation, one fermionic excitation. He has given dispersion relation and boson or fermionic. Read the options. In the option, he has given dispersion relation and or it's because of boson or fermionic. Now you have to answer it by what you call experience. What is the experience? This is bosonic, okay, and omega proportional to k, isn't it? In case of Debye cube law, okay. Now this one actually, this was next question, I think. Pick up. This was I think just question or something. First we shall do this question. Bosonic excitation of ferromagnet, okay. I told some spin wave or something. Is that okay? So they have dispersion relation. E is equal to pick up gamma k square, okay. Pick up. This is a bosonic. Okay, where E is the energy, K is the wave vector and all, okay. Assuming that system of such non-interacting bosonic excitation at low temperature T, specific heat of three-dimensional ferromagnet, okay. So D is equal to 3. The thing that he didn't mention, it is bosonic means mu equal to 0. You should take mu equal to 0. Otherwise, you can't do that Debye theory. Got my point? Okay, in one of the CSIR question, they mentioned mu equal to 0 actually. They carefully mentioned it's a bosonic with mu equal to 0. They mentioned. Then only it will follow phonon or photon statistics. You can do that theory, isn't it? Pick up. Now what happens? Pick up. S is equal to 2, D is equal to 3. We did that, what do you call, general theory, am I right? Specific heat proportional to T power D by S, am I right? It happened to be, okay. Now here it helps. Here it helps, okay. Specific heat proportional to T power, what is 3 by 2. Speak up. Now this question is needed to answer this one. T power 3 by 2. Now from that experience, I think I gave that one in the homework. Check that out. It is there in the homework as well as in the class also. I told that one. That some fermionic, bosonic excitation in the ferromagnet. Just check that out, okay, in the homework, okay, speak up. So now this is also bosonic, but omega proportional to k square, isn't it? Or energy proportional to k square. Which option? One bosonic, omega proportional to k square, another bosonic, omega proportional to k square. K. Is that okay? From the experience of this, I mean, this is very famous problem. Okay, I mean this spin waves, this ferromagnetic. Okay, because it's very famous. What you call a research area also. That's why usually, I mean, this experience should help you to do that one. Speak up. Got my point? Do the homework. I mean, briefly, at least briefly, do the homework. Okay.